230-volt motor can be powered by a single-phase 208-volt circuit, but it may not operate at its optimal performance. Electric motors are designed to operate at a specific voltage range. The nameplate of the motor will typically indicate the voltage range for which it is designed. For example, a motor with a nameplate voltage of 230 volts is designed to operate at a voltage between 220 volts and 240 volts. When a 230-volt motor is powered by a 208-volt circuit, the motor will receive less voltage than it is designed for. This can cause the motor to operate at a low speed and with less torque. In some cases, the motor may not be able to start or may run intermittently. It is not recommended to power a 230-volt motor with a 208-volt circuit unless the motor is specifically designed for this application. If you are unsure whether your motor can be powered by a 208-volt circuit, consult with an electrician. The motor's efficiency may be reduced when it is powered by a lower voltage. The motor's lifespan may be shortened if it is operated at a lower voltage for an extended period of time. Some motors may have a built-in transformer that allows them to operate at multiple voltages. If your motor has a transformer, check the nameplate to see if it can be powered by a 208-volt circuit. When considering whether to power a 230-volt motor with 208 volts, understand the fundamental principles behind motor operation and voltage requirements. Motors are designed to operate within a specific voltage range to ensure optimal performance, efficiency, and longevity. Supplying a motor with voltage outside of its rated range can lead to various issues, including reduced performance, overheating, and premature failure. The motor's nameplate provides critical information about its operating characteristics, including the rated voltage. It is essential to adhere to these specifications to ensure proper motor operation and prevent damage. Voltage is a measure of electrical potential difference representing the force that drives electric current through a circuit. Motors require a specific voltage level to establish the necessary magnetic fields and generate torque. When the supply voltage is lower than the rated voltage, the motor may struggle to produce sufficient torque to start or maintain its design speed. This can result in reduced performance, increased energy consumption, and potential overheating due to increased current draw. The relationship between voltage and torque in a motor is generally proportional. A decrease in voltage typically leads to a decrease in torque. This is because torque is related to the magnetic field strength, which is influenced by the voltage applied to the motor windings. When the voltage is reduced, the magnetic field weakens, resulting in low torque output. In addition to reduced torque, undervoltage can also affect the motor's speed. The speed of an alternating current (AC) motor is related to the frequency of the supply voltage and the number of poles in the motor. While the frequency remains constant in most power systems, the reduced voltage can affect the motor's ability to maintain its design speed under load. This can lead to speed fluctuations and reduced performance in applications requiring precise speed control. Furthermore, operating a motor at undervoltage can increase the risk of overheating. When the voltage is lower than the rated value, the motor draws more current to compensate and maintain its output power. This increased current flow can cause the motor windings to overheat, potentially damaging the insulation and reducing the motor's lifespan. Overheating can also lead to premature failure of other motor components such as bearings and capacitors. The motor's efficiency is also affected by undervoltage. Efficiency is the ratio of output power to input power, representing the motor's ability to convert electrical energy into mechanical energy. When the motor operates at undervoltage, it becomes less efficient due to increased losses in the windings and core. This means that more electrical energy is consumed to produce the same amount of mechanical power, resulting in higher operating costs and increased energy waste. In some cases, motors may have built-in protection mechanisms to prevent damage from undervoltage conditions. These mechanisms may include undervoltage relays or thermal overload protection devices. Undervoltage relays monitor the voltage level and disconnect the motor from the power supply if the voltage drops below a certain threshold. Thermal overload protection devices, such as thermal overloads, detect excessive current flow and disconnect the motor to prevent overheating. These protection mechanisms help to safeguard the motor from damage and extend its lifespan. However, relying solely on these protection mechanisms is not a substitute for providing the motor with its rated voltage. It is always best to ensure that the motor receives the appropriate voltage to ensure optimal performance and reliability. In situations where it is not possible to provide the motor with its rated voltage, consider using a step-up transformer to increase the voltage to the required level. A transformer is an electrical device that transfers energy from one circuit to another through electromagnetic induction. A step-up transformer increases the voltage from the input circuit to the output circuit, allowing you to provide the motor with its rated voltage even when the available voltage is lower. When selecting a step-up transformer, ensure that it is appropriately sized for the motor's power requirements. The transformer's kilovolt-ampere kVAR rating should be greater than or equal to the motor's kVA rating to prevent overloading the transformer. Also, consider the transformer's efficiency and voltage regulation characteristics to minimize losses and ensure stable voltage output. Before using a step-up transformer, consult with a qualified electrician to ensure that the installation complies with all applicable electrical codes and safety regulations. Improper installation or use of a transformer can create safety hazards and damage equipment. In addition to using a step-up transformer, another option for addressing undervoltage issues is to use a motor designed to operate at multiple voltages. Some motors are equipped with multiple voltage taps that allow them to be connected to different voltage levels. These motors typically have a nameplate that indicates the available voltage options. If your motor has multiple voltage taps, consult the motor's instruction manual or a qualified electrician to determine the correct wiring configuration for your application. When connecting a motor to a different voltage tap, ensure that the power supply is disconnected and that all safety precautions are followed. Incorrect wiring can damage the motor and create safety hazards. In some cases, it may be necessary to replace the motor with one that is specifically designed to operate at the available voltage. This may be the most cost-effective option in the long run, as it eliminates the need for additional equipment and ensures optimal motor performance. When selecting a replacement motor, consider the motor's horsepower speed, torque, and other performance characteristics to ensure that it meets the requirements of your application. Also, consider the motor's energy efficiency rating to minimize operating costs and reduce energy consumption. Always consult with a qualified electrician to determine the best solution for your specific application and to ensure that all electrical work is performed safely and in accordance with applicable codes and regulations. Ignoring undervoltage issues can lead to costly repairs, reduced equipment lifespan, and potential safety hazards. By understanding the effects of undervoltage on motor performance and taking appropriate measures to address these issues, you can ensure the reliable and efficient operation of your electrical equipment. Remember that electrical work can be dangerous, and it is always best to consult with a qualified electrician if you are unsure about any aspect of the installation or repair process. Firstly, always prioritize safety when working with electricity. Secondly, ensure the circuit is energized before performing any work. Thirdly, use properly insulated tools and personal protective equipment. Fourthly, adhere to all applicable electrical codes and regulations. Fifthly, if you are not comfortable working with electricity, consult with a qualified electrician. The information provided in this discussion is for general guidance only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrician for specific advice related to your situation. Additionally, always refer to the motor's nameplate and instruction manual for detailed information about its operating characteristics and voltage requirements. Understanding the importance of voltage in motor operation is crucial for ensuring the reliable and efficient performance of electrical equipment. By providing motors with their rated voltage, you can maximize their lifespan, minimize energy consumption, and reduce the risk of equipment failure. Always prioritize safety and consult with a qualified electrician when working with electricity to ensure that all work is performed safely and in accordance with applicable codes and regulations. The consequences of consistently operating a 230-volt motor on a 208-volt supply extends beyond just reduced performance and can potentially lead to more serious problems over time. It is helpful to understand the reasons why this situation can be detrimental to the motor. Motors are designed with specific insulation classes that dictate their ability to withstand heat. When a motor operates at a lower voltage than intended, it draws more current to try to produce the same amount of power. This increased current generates more heat within the motor windings. If the motor is constantly running hotter than its design allows, the insulation and the windings can break down prematurely. This breakdown can lead to short circuits within the motor, eventually causing it to fail completely. The bearings in a motor are also affected by undervoltage conditions. As the motor struggles to operate at its intended speed and torque, the bearings can experience increased stress and wear. This can lead to premature bearing failure, which can also cause damage to other motor components. Another issue that can arise from running a motor at undervoltage is cogging. Cogging is a phenomenon where the motor experiences jerky or uneven rotation, especially at low speeds. This is due to the interaction between the motor's magnetic field and the rotor. Undervoltage can exacerbate cogging, leading to increased vibration and noise. These vibrations can also contribute to premature wear and tear on the motor and the equipment it is driving. The motor's starting torque is also significantly reduced when operating at undervoltage. Starting torque is the amount of torque the motor can produce when it is first turned on. If the starting torque is insufficient, the motor may not be able to overcome the load and start properly. This can lead to stalling, which can further increase the current draw and cause the motor to overheat. In addition to the motor itself, the components that supply power to the motor can also be affected by undervoltage. For example, the wires and circuit breakers that feed the motor are sized based on the expected current draw. When the motor draws more current due to undervoltage, these components can overheat and potentially fail. This can create a fire hazard and disrupt the entire electrical system. It's crucial to recognize that simply because a motor starts and runs on 208 volts when it's designed for 230 volts doesn't mean it's operating safely or efficiently. The long-term consequences of this practice can be significant and costly. It is always best to provide the motor with the voltage it is designed for, or to use a motor that is specifically designed to operate at the available voltage. This will ensure optimal performance, efficiency, and longevity. If you're unsure about the correct voltage for your motor, consult with a qualified electrician. They can assess your electrical system and recommend the best solution for your needs. They can also perform voltage drop calculations to ensure that the motor is receiving adequate voltage under load. Voltage drop is the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can further exacerbate the problems associated with undervoltage. Therefore, it is important to minimize voltage drop to ensure that the motor receives as close to its rated voltage as possible. There are several ways to minimize voltage drop, including using larger conductors, shortening the length of the conductors, and reducing the load in the circuit. An electrician can help you determine the appropriate conductor size and circuit configuration to minimize voltage drop. Understanding the potential problems associated with operating a motor at undervoltage is essential for ensuring the safety and reliability of your electrical equipment. By taking the necessary steps to provide the motor with its rated voltage, you can avoid costly repairs, extend the motor's lifespan, and prevent potential safety hazards. Firstly, always refer to the motor's nameplate for its voltage and current requirements. Secondly, check the voltage of the motor terminals under load to ensure it is within the acceptable range. Thirdly, consult with a qualified electrician if you have any questions or concerns about the motor's voltage.